Okay, here we extend what we did previously. Here we're just saying the denominator is 0 and this is 0 or this is 0. So here and here, we already know that. If x is slightly bigger than negative 1/2, negative 6x minus 3 is less than 0, slightly less than 1/2, it's greater than 0. And what that does, in the way that we saw in the previous video, near x equals negative 1/2, which is here, and this vertical dotted line is the line x equals negative 1/2, we're going to get really large negative values whenever the value of x near negative 1/2 is less than 1/2, okay? Because that makes this factor greater than 0. We've seen that the rest of the factors in the function, here's the function, imply that the rest of the factors are negative, about negative 1.5, we said. You can verify that or correct it, but it's negative in any case. So we're going to get negative values as x gets closer to negative 1/2 through negative values. So go here, 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 here. The values will be negative. As long as we're close to negative 1/2, the values of the function are negative, and they get really big because, again, this factor, negative 6x minus 3, this factor is approaching 0. And on the other side, we get positives. So the graph is going to look like this on one side of negative 1/2, like this on another side of negative 1/2, or something like this. We can refine this idea, but this is the way the asymptote will pretty much look. Okay? Now, we have also an asymptote at x equals negative 6, and we've figured out how that's going to look. But let's look for a moment at what happens near the zeros of the function. Okay, remember we had a 0 equal to negative 1. If x is negative 1, that makes this factor 0. So the graph is going to go through the x-axis, or at least it's going to touch the x-axis at this point. In this case, it will go through. And at negative 3/4, we have another one. Now those zeros are pretty close together. If we consider at x equals negative 1, we know that y is going to be 0. All the other factors are going to be positive. If we put negative 1 into any of these other factors, we're going to get positive numbers. So that if x is slightly greater than negative 1, the factor 8x plus 8, which is the one that's 0 when x is negative 1, is going to be greater than 0. And the other factors are still going to be positive, so y is going to be greater than 0. So on this side of the negative 1, the x is going to be positive, or the y is going to be positive. Similarly, similar argument, and we can go through the detail. You can go through the details of the argument. If x is slightly less than negative 1, well, that makes 8x plus 8 less than 0. All the other factors still multiply out to be a positive number, so we're on the negative. We're into negative y's on this side of negative 1. We can do a similar analysis at negative 3/4, which arises from this factor, and we conclude that on this side of negative 3/4, the y is going to be positive, and on this side it's going to be negative, so that if we enlarge this interval between negative 1 and negative 3/4, at negative 1 we're going from a negative to a positive. At negative 3/4, as we go from left to right, we're going from positive to negative. So the graph has to look something like this in the neighborhood of those zeros. So we know that at negative 1 and negative 3/4, or between negative 1 and 3/4, the graph looks something like this. But when we get over to negative 1/2, which would be like right here, well, we have the vertical asymptote that goes down on this side and then comes down from positive values on the other side. So we're beginning to see how this graph behaves between negative 1, negative 3/4, and negative 1/2. We combine this behavior with this behavior, and we get what we're going to see in just a minute. Well, here's one attempt at the graph of the function. It had some strange behavior in it. I didn't draw it as well as I could, so let's kind of ignore this attempt. And here I corrected it. I corrected it twice, actually. Okay, so here's the function. We know what the x-intercepts are. They're at negative 3/4 and -1. So the x-intercepts are here. So this is -1, and I'm not going to label -3/4 and -1/2. But as we've just seen, we have zeros at -1 and -3/4, and then vertical asymptote at -1/2. We saw that the vertical asymptote goes this way from the left of x equals -1/2, and this way from the right of x equals -1/2. And we saw that the graph has kind of a tip of a parabola between x equals -1 and x equals -3/4 at the zeros. So we have our zeros, we have this asymptote. We also have an asymptote at x equals -6, and the analysis indicates that to the right of x equals -6, the x plus 6 is going to be positive, and everything else is going to be negative. So we're going to have a positive divided into a negative, giving us a negative, so the asymptote is down here. On the other side of x equals -6, x plus 6 switches to negative, which is going to make the division positive, giving us a positive asymptote. I've only drawn a little bit of that. Another aspect of the graph, and somehow I managed to smudge this in moving the board. Another aspect of the graph, and you can ignore this thing too. That's I'll explain that in a minute. It was an error. I made an error in graphing it like this. But for large x, what happens if x is large? Okay, if x is a very large number, then the -6 and the 8 and the -3 and the 6, being fixed numbers that are all less than 10 in magnitude, aren't going to make much difference. If x is 1,000,000, then this, and this, all four of these factors are close to either 1,000,000 for the two positive factors or -1,000,000 for the two negative factors. This gives us a positive number because these two factors will be negative if x is large, a large positive number. And these two factors will be positive, giving us a positive, and it's going to be a big number times a big number divided by a big number times a big number. It turns out that because these fixed numbers become irrelevant when x is really large, all we really have to worry about is the first, the number that's multiplied by x. So we'd have -8x times 8x here, which would be -64x. For large x, the numerator is going to be pretty close to -64x. For large values of x, the denominator is going to be pretty close to -6x. And actually, that's x squared. Doesn't matter, but we have -64x squared, -6x squared. And it doesn't matter if x is positive or negative. If x is -1,000,000, then these numbers are still really big. We can still ignore the fixed constants in these four factors, okay? And that turns out, well, the x squared is going to divide by the x squared. We're going to just end up with -64/6, which is 10 2/3. And it follows then that if x gets large, the value of the function is going to approach y equals 10 2/3. And if x gets big in the negative sense, the graph is going to approach 10 2/3 in the negative direction. So putting all that together, we get this. Now, originally I said, okay, we get something that looks like this. Here had the asymptote. Then I went and figured the y-intercept, which is 2 2/3, as you can easily verify by letting x equal 0. And this graph didn't go through 2 2/3. It just came down here to something that looks more like maybe 15. it has to come down to 2 2/3, then it'll come up from underneath. And you see I made the same mistake here when I started to draw this graph before I figured the y-intercept. Let that be a lesson. Figure out all the intercepts. Make sure your graph goes through all the intercepts. So going through all the intercepts, I have to come down below the asymptote. I can't go below 0 because the only places this can be 0 is where either this is 0 or this is 0. So I come down to this intercept, and at some point I've got to turn around and come back up and approach the y = 10 2/3 as a horizontal asymptote. Now that's probably more than you really want to know about this function, but if you can understand all that, you've got a real good picture of how rational functions behave.